Hi everyone, we are starting chapter 6, and if you're looking at the screen here, this is the section 6A homework in front of us. And I've had some students question how in the world we keep all these variables straight. Okay, when we start to get into normal distributions, we have the x variable. When we get into standard normal distributions, we have the z variable. And then when you start looking at these problems, they also throw a c at you in question 1. In question 3, you have the d and the z. In question 5, you have the x, and there's the probability notation. There's just a lot of variables being thrown at you. So I had some students question, how do we keep this all straight and what does it mean? Like in question 1, it says if z ... when they tell me that I'm working with a z, what should come to mind? What should I know? What does that mean? Okay, so I want to draw a picture for you here of, at least for me, what comes to mind. Okay, so we're going to have the x distribution, kind of the x world, and then we're going to have the z world over here. Okay, now a big thing that we're working with in chapter 6 is a normal distribution. Okay, they are, for the most part, going to flat out tell you that. Okay, a lot of information that we know when we have a normal curve, we only know if it's a normal curve. It has to be told that it's a normal curve. So if you're looking at problem 1, it says the word normal in here. Okay, we need to know that. In question 2, it says we're looking at a normal curve. We have to know that for this to apply. Okay, that you have to look for that key phrase that we're dealing with a normal or a standard normal. Okay, so the x distribution, think of that as the normal distribution. Okay, the normal. And the z is going to be referred to as the standard normal. Okay, so if you see the phrase standard normal, you're talking about the z world. Okay, so let's go back to x for the moment. For the x distribution, we're talking about a normal bell-shaped curve. Okay, it's highest in the middle and it tapers off on both ends. Okay, it's also known as a bell curve. Okay, the highest peak of this bell curve is going to be occurring at your average, okay, at mu. And that mu can be any number. Okay, it could be 5, it could be 10, it could be 27,000. Okay, it's the average for whatever that story is going to tell you the average is. Okay, so there's no restriction on what that mu, that average can be. Okay, in addition, an important piece of information for this curve is your sigma, your standard deviation. Okay, and again, that sigma could be any number, whatever the story tells you it is. Could be 2, could be 27, could be 35.8. Okay, it could be whatever number. Okay, and that's going to tell you, that sigma is going to tell you how spread out or how clustered close together this bell curve is. Okay, but no matter what, big picture, if you have an x distribution, if it's normal, it's going to be in general a bell-shaped curve like this. Mu, your average, that number is going to be dead center, and this curve is going to be perfectly symmetrical on each side. Okay, so that means if you folded both sides together, everything will line up. Okay, so that is a normal curve. So the pieces of information that you should know is mu is in the middle, it's a bell-shaped curve, and it's symmetrical. Okay, now the z distribution, what is that? Okay, so it's referred to as a standard normal distribution, standard normal, okay, and it's going to look pretty similar for our purposes to an x curve. Okay, it too is going to be bell-shaped, it too is going to be symmetrical. Okay, so it's going to look something like this. Now it's not the same curve, so I drew it at a different height, but it's still a bell curve. Okay, the thing that's kind of magical or important about the standard normal curve, the z curve, is that just like the x curve, the mu is in the middle, but in this case we know that the mu is 0. The mu will be 0 every single time in a standard normal distribution, which is really nice because we have a table for that. Okay, and the sigma is 1. So with that combination, we can have a table that some smart guy who knows calculus, who knows how to find areas under the curve, he can tell us areas under the curve to figure out probability for this. That's what's so powerful about the z-curve, is that we can use this smart calc guy to come up with this probability table for us. Okay, so we like the z-curve because we have a table for that. The question though is, story problems are typically given in the x world, the normal distribution. So how do we go from this x world over to this z world? You know, how do we translate from one world to the other? And how we do that is by using a formula. Okay. Now, before I get to the formula, let's look at these problems over here. So in question 1, it says if z is a random variable from a standard normal distribution. Okay, so the big clue here is that we're looking at a standard normal distribution. It says that in the problem. So your picture in your mind should be on the right-hand side of the screen there, that z-curve. So right away, you know that it's a bell-shaped curve, mu is 0, sigma is 1. Okay, you know that right away because it's a standard normal distribution. Okay, now they talk about this c value, okay? So just like in problem 1, if you scroll down and look at problem 3, very similar. We're talking about a z-curve, okay? And it's talking about this z value being stuck in between negative d and d, okay? The d in this problem, the c in this problem, they're giving you values. If you look at my z-curve here, oops, they're giving you values along the bottom. So in problem 1, when they talk about c, they're talking about a c right there and a negative c right here. They're giving you values along the x-axis, okay? If you're looking at question 3, when they're giving you negative d and d, again, they're giving you values across the x-axis. And you know that they're going to be symmetrical because this is just a number line, 0 is right in the middle, so negative d has to be a certain number of steps to the left, and positive d has to be a certain number of steps to the right, okay? Scrolling through here some more, you know, in question 5, okay, so there it says if x represents a variable from a normal distribution. So now we're in the first picture. We're not in the standard normal, we're just in the regular normal. If x is less than 7.4, if x is less than 7.4, okay, so that means along this x-axis along the bottom here, you would plot a 7.4, okay. Keep in mind this bell curve is perfectly symmetrical, okay, and 100% of the area under the curve is what's represented here. So if we're talking about the probability of this guy being equal to 0.38, that's less than 50%. So if I was going to put that 7.4 somewhere, even though I don't know what the average is, I know the 7.4 has to be somewhere over here, because when I would color in that area to the left of 7.4, an area under the curve is equated to probability. If that probability, that area, is 0.38, that's less than 50% of the curve. So that's how I knew to kind of bump that 7.4 to the left, okay? So this is all about drawing pictures. You should be sketching a whole bunch of little bell curves here and shading, okay? And it will start to be very, very repetitive, okay? Area under the curve is 100%. Half the area under the curve is 50%, so then you need to kind of place things appropriately, okay? Looking for other variables here, you know, looking at question 7, we're looking at find the probability, well, let me back up. If x represents a variable coming from a normal distribution, so we're in the x world again, we're in this picture. So they tell me in this case that the mu is 4, okay? So I know in this case, let me erase this stuff here. My eraser is frozen, so ignore that. But if I knew that the mean was 4, that means 4 would be dead center. Okay, in that case, the mean would be 4 being dead center. and you want to find those x's that are more than 5.6, you would write that 5.6 even further to the left and then shade in that area being the 0.35. So the key features that you should keep in mind are the mu is in the middle, always, whether you're talking x world or z world. The x world is talking about a bell curve. Probability and area under the curve should be linked together. Z curve is a bell curve. Mu is in the middle, but in that case, we know that mu is 0, okay? And to go from one, and I apologize, my pen is kind of frozen here. It's not letting me write. But to go from the x world to the z world, we're looking at z is equal to x minus mu over sigma. Z is equal to x minus mu over sigma. Hope it is letting me right there. Okay, so that's a calculation that can let you change an x into a z, and you have to use the mu and sigma from the x world. Now, why are we doing this? You know, why do we have this x and this z world? Why do we have these two different worlds? In the current situation that we're in, think about coronavirus for a second. If you look at data and you say that there were 200, or let's be dramatic, let's say 2,000 coronavirus cases, okay? You need some situation behind that number, okay? Are you talking about 2,000 coronavirus cases in Ohio? Are you talking about 2,000 coronavirus cases in New York? Are you talking about it in one small city? Are you talking about it in one small town? You need some context, okay? Because 2,000 cases in New York is not the same severity as saying 2,000 cases in a small town, okay? And what we're doing here in going from X to Z is we're trying to standardize scores, okay? If you go look up data for the coronavirus rates right now, they're trying to standardize things by equating all cases by being per, I think it's 100,000 that they're saying right now. You can look it up for Ohio, and they say that there's, you know, for this county, there's this many cases per 100,000. For this other county, there's this many cases per 100,000. So they're trying to get them all on the same level playing field, okay? And that's what we're kind of doing with this Z, the standard normal, okay? Instead of just dealing with data, they're changing it and they're counting standard deviations, okay? And you can kind of think of that like with this coronavirus cases as putting them as on the same measuring field as per 200,000 or per 100,000, however you want to standardize it, okay? So hopefully that helps out with the different variables that you're seeing here, okay? Don't get too bogged down by that, okay? The Z's, you're talking about this picture. The X's, you're talking about this picture. When they're talking about, you know, lowercase b and lowercase c and all those, they're talking about hypothetical numbers that are along the x-axis, and you're just plotting them there, okay? They're just constant numbers there, all right? So hopefully that helps with the variables here in section 6A, and keep plugging away.